Okay, next we are going to address these two problems. First one, when a quotient ring R by I is a integral domain. Similarly, under what condition a quotient ring is a field? Okay, before that we have two more definitions. First one, prime ideal. An ideal not equal to entire ring and xy belongs to ideal implies x equal to I or y equal to I. This is the definition of prime ideal. Then this result says that an ideal is a prime ideal if and only if R by I is a domain. Okay, first we are going to establish the second part. That means R by I is a domain, then I is a prime ideal. Okay, R by I is a domain means what? R by I is not equal to 0. R by I is not equal to 0 means R by I contains more than one element, right? Then I is not equal to R, because if I equal to R, then it is clear that R by I is equal to R by R, which contains only one element. Next we have to show that xy belongs to I implies x equal to I or y belongs to I. Our assumption is R by I is a domain. That means R by I has no zero divisors. That means x into y equal to 0 implies x equal to 0 or y is equal to 0. Okay, already we know that cosat x into cosat y is equal to cosat xy, and cosat xy equal to 0 implies xy belongs to I. So xy belongs to I implies what? Either cosat x equal to 0. Cosat x equal to 0 means x belongs to I. So x belongs to I or y belongs to I. So we can conclude that if R by I is a domain, then I is not equal to R and xy belongs to I implies x equal to I or y belongs to I. So this I is a prime ideal. Conversely, we have to show that if I is a prime ideal, then R by I is a domain. Okay, that is very easy because I is a prime ideal means I satisfies this condition. Okay, already we have seen that I is not equal to R means R by I is not equal to 0, right? Then next we assume that xy belongs to I. Xy belongs to I means what? Xy belongs to I means the cosat xy equal to 0. Okay, so cosat xy equal to 0 means cosat x into cosat y equal to 0. So cosat x into cosat y equal to 0 implies what? X belongs to I or y belongs to I. X belongs to I means cosat x equal to 0 or this means cosat y equal to 0. So we can conclude that I is a prime ideal if and only if R by I is a domain. Okay, next we are going to address the question under which condition R by I is a field. Okay. So before that we have one more definition, that is maximal ideal. Maximal ideal means if J is an ideal which is greater than I, then J must be R. That means in between I and R there is no other ideal. The next result says that an ideal subset of R is maximal ideal if and only if R by I is a field. So first we are going to establish the second part. That means R by I is a field, then I is maximal. R by I is a field means R by I is not equal to 0. In previous result we have seen that R by I is not equal to 0 implies I is not equal to R. Since R by I is a field, every non-zero element x belongs to R by I, where there exists a non-zero y belongs to R by I such that cosat x into cosat y is equal to 1, and we know that this is equal to cosat xy, and we consider a non-zero element. So this is not equal to 0 means x is not belongs to I. Similarly, this y is also non-zero, so y is also not belongs to I. Clear? Also we know that two cosets are same if their difference belongs to I. So xy belongs to I. So this means every x not belongs to I, there exists a y belongs to R. Of course y is not belongs to I but y belongs to R, such that xy minus 1 belongs to I. We have to show that this I is maximal. Okay, so we just assume that suppose there is another ideal J which contains I, then we have to show that J equal to R. Here it is proper subset. J is superset of I. Okay, so we choose x from J minus I. Of course, x is not belongs to I, right? We know that if x is not belongs to I, there exists a y is not belongs to I, such that xy minus 1 belongs to I. So we can find a y which is not belongs to I such that xy minus 1 belongs to I, and I is strictly subset of j. But xy belongs to j because x belongs to j. So x belongs to j and we can treat y as an element of R, then we know that y into x belongs to j because j is an ideal. Okay, then it is clear that this sum belongs to j because xy is already belongs to j and xy minus 1 belongs to I is a subset of j, so this also belongs to j. So there minus of its additive inverse also belongs to j, so this whole sum belongs to j. Okay, and this whole sum is nothing, it is equal to 1. So 1 belongs to j. 1 belongs to j means j equal to R. That means there is no ideal in between I and R. That means I is maximal. Next we have to show that I is maximal, then R by I is a field. So under the assumption I is maximal, we have to show that R by I is a field. We have to show that every non-zero element in the ring R by I has an inverse. Okay, so we consider a non-zero element from R by I. This x is non-zero means x not belongs to I. So we can easily show that this collection I plus Rx is an ideal of R. But it is clear that I plus Rx is a strict superset of I. That is because this x is not belongs to I, that means x is outside I, and this ideal contains x. Since I is maximal, we know that this ideal is equal to our entire ring R. A ring contains a unity, so 1 belongs to I plus Rx. 1 belongs to I plus Rx means 1 is of the form I plus Rx for some I and some R. That means 1 is equal to m plus Rx for some m belongs to I and R belongs to R. Okay, since 1 equal to m plus Rx, their cosets are same. So coset of 1 is equal to coset of m plus Rx. And using our coset addition, we can split this like this, coset m plus coset Rx. And what about the coset m? Coset m is 0 because m belongs to I. Okay, and what about this one? This is equal to coset R into coset x. So we can conclude that coset R into coset x is equal to our identity. So this x has an inverse, or this x is a unit. So we can conclude that every non-zero x is a unit. So R by I is a field. This remark is trivial. A maximal ideal is a prime ideal because we know that I is maximal means R by I is a field. Field means it's a domain. R by I is a domain means I is prime. That's why maximal ID is a prime ideal.